Okay, hello everyone. My name is Scott. This is Calculus 1. Tonight, this is class 7A, and this evening we're going to talk about logarithmic differentiation. So last time I did implicit differentiation, and then I totally blew the algebra for one of the proofs, so that'll be the first thing we fix tonight. And then I got sick over the weekend, so I didn't get anything done. Which was a strange, but I'm feeling better starting, this afternoon, and I'm very happy about that. You don't care. Well, you might care, but I shouldn't be sharing. Anyway, so what we want to do today, this is another one of those implicit differentiation tricks. So just like last time I mentioned that everything that's kind of coming is these implicit differentiation tricks. And the use of doing implicit differentiation very important here. But what we're going to do is show that there's a whole bunch of algebra that you could do before you even take a derivative. And that's really the key. The key is the algebra, is to know that you can do algebra first, and then do and then do the derivative. So let's see if this still works. There it is. So as I said, tonight we're going to finish the power rule for rational exponents. That's not log yet. And then we'll do this again with log. So we'll kind of clear everything up there. Okay. As usual, there is chat in Discord. There is chat in Twitch. And all of that good stuff. Okay. Are there any questions before we begin? Let's see. Pull up the stream manager. Make sure that's visible. Okay. So let's look at what we're doing. This is, again, finishing what we did last time. We'll let P and Q be integers, Q not equal to 0. And we want to show, so this is the power rule here. Power rule. For rational exponents. Okay. So what I'm going to do here is I'm going to let y equal x to the pq, and then I'm going to take the q's power of both, and then I'm going to apply the power rule. So this is what this is going to look like here. So let y equal x to the p over q. Then raising both sides to the q. The q power. I get y to the q equals x to the p over q to the q, which is exactly the same as doing x to the q p over q. So the q's will cancel, and I get x to the p. So now what I'm going to do is take the derivative of both sides with respect to x, and I get d over dx of y to the q equals d over dx x to the p. All right. So now what I'm going to do is apply the power rule to both, because I know the power rule for integers. I get qy to the q minus 1 equals px, dy over dx equals px to the p minus 1. because I did the chain rule there. That's where the dy over dx came from. And that gives me and then now what I'm going to do is I'm going to divide both sides by this term here. And now this algebra, which I totally messed up last time, comes into play. This is a nightmare in algebra. So what I get is dy over dx equals p. That is not a pretty looking p. P x to the p minus 1. And then I'm going to take, q y to the q minus 1. And now what I'm going to do is go grab a quart of Pepto-Bismol. And I'm going to do this nice little, beautiful, easy piece of algebra. Right? So this is going to become x to the p minus 1, q to the y to the q minus 1. And in the end, what I want is going to be, what I want in the end is I want x, it should be red, x, p over q, which I have, x to the p over q minus 1. Okay, now recall that y equals x to the p over q. All right, so what I'm going to do here is what I'm going to have here is I'm going to have x, and what I'm going to do on this thing here is I'm going to move the y up to the top before I sub it in. So I get x to the p minus 1, y to the negative q plus 1. Okay. And then what I'm going to do is sub in for y here. So I'm going to wind up with p over q, which just hangs out, x to the p minus 1, x to the p over q, to the negative q plus 1. Okay, so this right here, what I did was sub in for y. And now when I do this, I'm going to remember this time to distribute both terms, which I didn't do last time, like an idiot. And what I'm going to get is I'm going to get p over q, x to the p minus 1. We're just going to leave you there. I'm going to pull this exponent into front since I'm multiplying. I'm going to get x to the p over q times negative q plus 1. And this time, I am remembering to distribute properly. So this will become negative q p over q plus p over q. Okay, and now what's going to happen is the q's are going to cancel. So now what I wind up here is p over q. Oops, that equal sign is way too low, way too high. Equals p over q x to the p minus 1 x to the negative p plus p over q. And that is going to equal this. Now I'm going to add the exponents together, and I get p minus 1 minus p, thank you, plus p over q. The p's are going to cancel. and I wind up with P over Q minus 1, which is what I wanted. Move you up there. So, P over Q, x to the P over Q. So the derivative, so d over dx of x to the P over Q equals P over Q x to the P over Q minus 1 as long as that is defined at that particular x. And notice here, I did not assume that x was greater than 0. Okay, so obviously if I'm talking about square root, well, that's not defined because we're just talking about real numbers for the moment, but it doesn't care, right? And so what did I do here? All I did was, first of all, I remembered to distribute this properly, which is what I messed up last time. But the other thing I did here is I created this y, right? I made y happen. And then I did some algebraic manipulation. Okay? So what did I do? What were my key steps? I created a y. Did some algebra to both sides, implicitly differentiated, and when I implicitly differentiated, after I implicitly differentiated, I solved for dy over dx, remembering to sub back in for y. Because I created y, I have to sub him back in. So how do we feel about that 1 to 5? Besides the algebraic, besides the Pepto-Bismol required for this. How do we feel about what I did there, 1 to 5? Okay. All right. 5 poll seems to be down. So if you're doing the chat in if you're doing the chat in Discord, thank you. Please just go ahead and type your number. All right. Well, again, there's a whole bunch of algebra here that is just very unpleasant with these terms in the top in the exponents. As I said, I messed it up last time. But the overall theme is this. I create a y, I do some algebra, and then I implicitly differentiate. And we can use this kind of, if we use logarithms, we can do this trick again and again and again and again. And then we're going to use it later to prove the inverses for things like sine and cosine and stuff like that. So you can use this trick. The basic trick is not logarithmic differentiation. The basic trick is create a y and do some algebra. In fact, I actually want to change the name of this thing here, right? I don't want to do this. I want to do create a y and do some algebra. That's really the key idea. All right? I make a y, and then I do some algebra. All right, so let's look at the algebra we want to use. This is the big algebra trick for this thing. By the way, this is section 3.3 in your textbook if you're following along in the book. We skipped, we're coming back to them, but we skipped the sections on implicit differentiation and linearization. So if you're following along in the textbook, you'll wonder what happened to, I'm sorry, not implicit differentiation. We did 2.6. We're skipping 2.7 and 2.8 for a moment, and we're coming right back to them. They're both extremely important sections, and we will be doing them, but we want to do this trick first. Okay? And they're also involving implicit differentiation. Anyway, so we skipped 2 sections, but we're coming back before the test. Some people do those 2 sections first before the test, but I'm not. Okay, so the big algebra trick for this section, 3.3, is the following. That the log, what just happened? Did I keep my stuff? I don't know what just happened, but okay. That was weird. The big algebra trick for this section. And it is as follows. The log of a to the x or y, or I don't even want to use x. The log of a to the q. Why not? The log of a to the q equals q log a. Right? And this is algebra. Right? So calculus cares about what moves, but algebra doesn't. Right? Algebra is algebra. It works. Right? So this is true. So this works if Q and A are moving or not. Doesn't care. It doesn't care whether or not the A and the Q move with X. Okay? Because the rules do. Remember the rules. The power rule cares what moves. The power rule works only when the base moves and the exponent is constant. Okay? And the exponential rule only works when the exponent moves and the base is constant. And the exponent rule only works okay? So for example, let's look at an example of this. For example, okay, d over dx of x to the fifth equals, by the power rule, 5x to the fourth. D over dx of 5 to the x equals, by the exponent rule, the log of 5 times 5 to the x. Okay. So here, base moves, exponent constant, power rule. All right. Here, exponent moves, base is constant, so exponential rule. How do we feel about that 1 to 5? I got a power rule and I got an exponent rule, and depending on what's going on, tells me which one to use. All right, so when x is in the base and the exponent is fixed, so the base is moving and the exponent is fixed, I use the power rule. When the base is fixed and the exponent moves, I use the exponent rule. Okay. But what about this? What do I do if both move? Well, remember, algebra doesn't care. Now, it should be noticed that algebra changes domains, but it doesn't care about these other things. So, example. Consider f of x equals x to the x. All right, so let's talk about this function. This function is kind of cool, and it's on your packet. This particular one is one of the walkthrough proofs on the packet for this week. But let's look at this function, because this function is very interesting. Let's go up to Desmos here. Let's close out all of these things. Let's go to our graphing calculator. Now let's look at this function. Oops. Screen 2. All right, so here's this function here. Let's go to x to the x. Now, notice this function is not defined everywhere in the negatives, because when I have it exponent, I actually only define that on rational numbers if x is less than 0. X to the pi doesn't mean anything if x is less than 0. It's undefined. Okay? And then you get these weird, and the reason it's undefined is you have this weird behavior where if it's an odd exponent, it's below the negative, and if it's a positive exponent, it's up here. But let's look at what happens with x if we restrict ourselves to x being greater than 0. Because this function is actually kind of cool. Let's see. I do shift, right? No? There it is. This function is actually really cool on the positives, right? This right here, as I go towards 0, okay, we have some interesting things about this function. So let's just do it a little aside. So x to the x, f of x equals x to the x, where x is greater than 0. All right, that's where we're going to define this thing. So what we're going to do, so f is a function. We are going to define this f as a function on open interval 0 infinity. And it doesn't matter. We'll just go to everything. Even though it only gives positive values as the output, we'll just go to everything. All right. So let's do some interesting things about this function. So I want to do a screenshot here. So let's go back. Okay. So let's talk about some interesting things about this function. Let's see. All right. The first thing that's kind of cool about this function is what happens as I approach 0. All right, so the limit as x goes to 0 from the right of x to the x equals 1. Okay. And the limit as x goes to infinity of x to the x equals infinity. Now, it has a minimum at a very interesting place. Okay? Its minimum right here, if you look at it, the place where you have a horizontal tangent line, that is the number 1 over e. Which is weird. Why is that? Where's 1 over e comes from? So this has a minimum at x equals 1 over e. We're going to get into why that later. But that's kind of an interesting thing that's going on here. Okay? So this is a rather interesting function, just as a function in general. And x to the negative x is also an interesting one on its own. So its reciprocal is very interesting too. Okay. Well, so how do we take the derivative? Well, what we're going to do, okay, is the following. We're going to do our steps. So our steps, which I wrote up here, where we're going to create y, do some algebra, implicitly differentiate, and solve. So I'm going to create y. My y is going to equal x to the x. So create y. And 2, I'm going to do some algebra. In particular, I will take the log of both sides. Okay, so what I'm going to wind up with is the following. This should be in purple. This is kind of a purple thing. Oops. So I'm going to do ln of y equals ln of x to the x. Now, why did I do that? The reason I did that is because I want to leverage this little toy. I want to leverage this little piece of algebra. Okay? Because remember, log doesn't, it's just algebra. Log doesn't care whether x is moving or constant. Now, it definitely cares about the fact that the base is positive, right? I have now said, the only thing I could say about this is I've made x and y both positive. Okay, that trick only works when x and y are both positive. But for the moment, no, that's fine, right? There's my domain. There's my code. I could even restrict this if I wanted to. If I wanted to make that 0 infinity. Because remember, the natural log is not defined for negatives. This is not a course in complex numbers. All right, so let's see what happens here. If I do that, then this x can come in front. So that means the log of y now equals x log x. And notice no calculus has been done yet. Now I'm going to do, so this is algebra, create algebra, algebra. Now I'm going to differentiate both sides. And I get d over dx of ln of y equals d over dx x times ln of x. All right, so here what I'm going to do is this is going to be 1 over y times dy over dx, right? That's the implicit. I'm changing something here. This right here is a y. I need to multiply it by dy over dx. On this side, I'm going to need a product rule. So on the right, we're going to get the derivative of the first times the second plus the first times the derivative of the second. Now I'm going to just do, now I'm going to clean this up and I get 1 over y times dy over dx equals 1 times ln of x plus x times the derivative of that, which is 1 over x. Now, I'm going to need to be careful when I cancel here. So I'm going to get 1 over y dy over dx equals ln of x plus, now these x's when they cancel leave a 1 because they're multiplication there. So be careful of that. And 1. So what did I do? Now I took the derivative of both sides. The fourth step is to solve for dy over dx. Well, that's easy. I just multiply y by both sides, right? So now we're back in algebra land. And we get dy over dx equals 1 over y, I'm sorry, just y times the ln of x plus 1. And now I sub back in y. And I get dy over dx equals x to the x times ln of x plus 1. Okay. So how do we feel about that 1 to 5? Okay. All right, so notice that most of this work, I mean, besides the fact that I was super careful about my derivative, most of this work is really algebra. Okay. Let's do another example. Let's do another example. Let's do d over dx of x to the cube root of x squared. Let's just make it unpleasant. All right. Okay, now step 1, let's create a y. So the solution is let y equal. Let is a very powerful word in mathematics, isn't it? Let. Let it be. But it's more like, it's less, let it be, Beatles, and more like let there be light, right? Let. Very powerful word. This is why people like mathematics, because they get to say let all the time. Let y equal x to the psychotic thing that's on top. Okay? All right, so. Okay, then ln of y equals the cube root of x squared times the natural log of x. Okay? And I'm going to simplify this thing out right here. And I'm going to let this be, I'm going to do the x to the 2/3 power times ln of x. All right, so it looked intimidating, but it wasn't really. This has more bark than bite. Now I'm going to take the derivative of both sides, so I'm going to wind up with 1 over y dy over dx equals the derivative with respect to x of x to the 2/3 times ln of x. Well, that's going to be a power rule. And I'm going to wind up with 2/3 x to the 2/3 minus 1. Oop, I didn't write the derivative, did I? I'm skipping a step. Points off Scott's paper. Product rule, not power rule. Plus x to the 2/3 times d over dx ln of x. I'm already wanting to do it without writing out the steps, and then of course I'm making a mistake. All right, so let's carry this 1 over y dy over dx equals, now I'm going to use the power rule, 2/3 x to the 2/3 minus 1, which is going to be negative 1/3, times ln of x plus x to the 2 over 3 times x to the negative 1, which is the same thing as 1 over x. And then I'm going to add some exponents. So I'm going to wind up with 2/3 log of x to the negative 1 over 3 plus x to the negative 1 over 3. Ooh, that factors. I'm not going to do it, but it does. Okay. And now I'm going to deal with the y. So now I get dy over dx equals y times the quantity 2/3 ln of x to the negative 1 over 3 plus x to the negative 1 over 3. And then I sub back in my y, which was x to the cube root of x squared times the quantity 2 over 3 ln of x to the negative 1 over 3 plus x to the negative 1 over 3. And there's my answer. So 1 to 5, how do we feel about this one with all this crappy algebra? Okay, and notice that the trick is really the algebra for these. Okay. It's really an algebra. It's a mess, but it's an algebra mess. Right? The calculus mess, there was only a product rule in here, and then a power rule right there. It was really an algebra. Oh, and by the way, on this side, so since we do this so often, you can just write 1 over y dy over dx. We do that so much that you don't have to be careful about that. Everyone knows exactly where that came from. But you can skip it. I'm trying not to, but I did here. Okay. All right, well, we can use this to prove that power rule finally, the power rule in general. So, but note there's a limitation. This particular proof requires that x be greater than 0. So it doesn't work for everything, right? So let's prove that if x is greater than 0, d over dx of x to the c equals c x to the c minus 1 for any real c. So I've already done it. So let's do a little power rule checklist. What did we do here? Let's do a little power rule checklist up on the side. Power rule checklist. We proved, okay, for any x and integer and positive integers d over dx x to the k equals k x to the k minus 1 using binomials. In order to do that, we use the binomial theorem and definition of the derivative. Okay, that was the first one we did. The second one we did was for any x where kx to the k minus 1 is defined, and any integer k, not just positive integer, any integer k, d over dx, x to the k equaled kx to the k minus 1. To do that, we used the reciprocal rule, which we got from the chain rule. So we used the reciprocal rule and power rule for positive integers. Okay. All right, and then what did we do? Well, now we did it for any rational integers. And any rational coefficient, rational exponent. Oops. C d over dx, x to the c equals k c cx to the c minus 1. That was done. So we used, what did we use for that? We used implicit and integer power rule. All right, and that's this one right here. So now what we're going to do it for x greater than 0 and any real c, d over dx, x to the c equals cx to the c minus 1. And we're going to do that used logarithmic. But note, x has to be greater than 0 for this to work, but for it to be defined anyway, x has to be greater than 0. So this is our power rule checklist, okay? So we've got x for k positive integers. We use that to get this. We use that to get this. And then we use these two are in a chain. This one stands alone. Okay. So let's do it. Strategy. Let y equal x to the c. Take logs and differentiate. Okay. This should actually all be in blue. Okay. So let's do it. So y equals x to the c. So implying ln of y equals c ln of x. Okay, now I take the derivative with both sides, allowed since x is greater than 0. Now I take the derivative of both sides, and I get d over dx of ln of y equals d over dx c ln of x. And notice here c is a constant, so I could just use the constant multiple rule. So I'm going to wind up with 1 over y dy over dx equals c times x to the negative 1. Okay, I'm going to move the y over, and I get dy over dx equals y times c. I'm going to put, for reasons that will become apparent in just a moment, I'm going to do this. C times y times x to the negative 1. And note, y equals x to the c. So now I wind up with dy over dx equaling c x to the c times x to the negative 1, and that is the same thing as c x to the c minus 1. How do we feel about that proof 1 to 5? There's something kind of black magic about that, isn't it? A little voodoo. There's voodoo, right? Voodoo proof. I don't know. So, sometimes that's not politically correct. Apparently, it's supposed to be voodoo, but then, I don't know. Voodoo proof works fine. Okay, that's kind of a weird thing. It just comes kind of from nowhere. But that's it. Let's do the exponentials. And note here, x doesn't have to be greater than 0 because x is in the exponent. Okay. So we're just going to let y, we're going to do the exact same thing. Let y equals c to the x. Then ln of y equals x times ln of c. C has to be greater than 0, not x. Okay, so now what I'm going to do, I take ln of y here, and I'm just going to do the derivative. So it's going to be dy over dx times 1 over y equals, and then this right here is not a product rule. Ln of c is a constant. That just comes out by the constant multiple rule, right? And the derivative of x is just 1. So now I'm going to multiply y over by both sides, and I wind up with dy over dx equals ln of c times y. And then remember that y equals x to the c, so I get ln of c times x to the c. How we feel about that? 1 to 5. Okay. Well, let's do the cheap proofs. Cheap product rule proof. Okay? Don't use these on the test because they are cheap proofs, right? Here's the product rule. All right? I'm going to have that u show that d over dx of u times v equals du dv times, I'm sorry, not dv, du dx times v plus, that's a v, by the way, plus u times dv over dx. Proof. When u v greater than 0. Proof. Okay, so I've got y equals u times v. That means that the ln, the log of y, equals the log of u v, which equals the log of u plus the log of v. All right, now I'm going to apply now I'm just going to take the derivative of both sides. So this is going to be 1 over y dy over dx equals, well, 1 over u du over dx plus 1 over v dv over dx. Okay. So I'm just going to multiply through, and I get dy over dx equals y times 1 over u du over dx plus 1 over v dv over dx. But recall, y equals u times v. So I wind up with dy over dx equals u times v over u times du over dx plus u times v over v dv over dx. And I have a cheap log proof for the product rule. Oh, I got time. I'll just do it. Well, let's do a cheap LM proof of the quotient rule. Oh, wait. Dang it. I can't remember what the quotient rule. Which one comes first? Oh, goodness. I never remember this. Huh. How do I remember this? Well, I can't use this as a proof, but let's see if I can use it as a mnemonic tool. All right? So I don't remember what it was. Which one came first? Which one was second? Where'd the minus go? I don't remember. Let's see if I can remember it with a little mnemonic device here. Let's let y equal u over v. Okay? So what's going to happen here is that an ln, so let, I write the word let here? I didn't. So the log of y equals the log of u over v. Well, the log of u over v is the log of u minus the log of v. So when I take the derivative of both sides, I'm going to wind up with 1 over y dy over dx equals 1 over y du over dx. I'm sorry, not 1 over y. 1 over u du over dx minus 1 over v dv over dx. So what gets that other term? Right? The negative has to go with dv over dx. Because when I took the log, it was on the bottom. Ah, that's right. Now I remember. So it was this is going to be du over dx times v minus u times dv over dx all over v squared. Right? Because that's where that minus came from. Aha! Okay. Well, let's just finish it. So I've got dy over dx equals y. Y times 1 over u times du over dx minus y times 1 over v times dv over dx. That should be a v. It looks like suspiciously like a u. Okay. All right, so what do I do? Well, I just kind of multiply through by, I sub back in. So recall y equals du, u over v. And I wind up with the following. So I've got u over v times 1 over u times du over dx minus u over v times 1 over v times dv over dx. Okay, well, those things cancel, but these don't. Now I'm going to have a v squared on the bottom here. So I wind up with 1 over v du over dx minus u times dv over dx all over v squared. Well, I'm going to take a common denominator here, and I get v du over dx over v squared minus u dv over dx over v squared, which equals v du over dx minus u dv over dx all over v squared. Okay? How do we feel about that cheap proof? One to 5. Okay. So today, what we did was we finished off that ugly thing that I had before. All right. Okay. And then we went over this trick. And the trick, remember this trick, the big deal for this trick is this little piece of algebra. And then I just follow the steps that I had before. I create a y, I do some algebra to both sides, I implicitly differentiate, and I solve for dy over dx. All right. Next time, what we're going to do is we're going to start looking at related rates problems. So the key takeaways are it's implicit differentiation with this one piece of trick. All right, next time, we'll start related rates problems. This will be related rates 1. We're actually going to spend a little bit of time in related rates. Does anyone have any questions? Okay, well, if that's the case, then that's it for me. 5 minutes early today. And I will see you all on Wednesday. Thank you for coming.